Here are some other types of equations that can be solved using a computer multi-equation solver. This one is the exponential, where one of the terms is an exponential term. In this example, we'll look at the nuclear decay function, and here are some sample values. I've left n to equal a number with a large amount of decimal places, so as to monitor the accuracy of this method, and also because this is how it will be operated upon while still in the computer, until it eventually gets rounded. This is function f of this nuclear decay equation, which is equal to 0 whenever the nuclear decay equation is solved. So we'll substitute all the numbers into it, and also substitute lambda equals 0 into it. This is f0 when lambda is equal to 0. And similarly, we can find f1 when lambda equals 1. And then we need to find f2 for lambda equals 2, since we need 3 points to calculate this curve. And so this is what our reconstructed function f should look like, as an exponential equation. And we need to get the variables a, b, and c from the values of f0, f1, and f2. And we need an intermediary value called L, which is this messy expression. And so this is the messy number that L is equal to. And B can be calculated from it and is equal to this number, which is equal to the value of minus t. And this is the equation to find A. It corresponds to N0, the initial amount of radioactive material. And this is how to calculate C, corresponding to the final amount of radioactive material, either in mass or in moles. And here is a graph of this function passing through all the points, including 2 checking points, to make sure that the curve is really an exponential function. Here you can see another polynomial function that can pass through 4 of the points, but missing the 5th. This curve is shown in white. And now to check that the equation really is equal to this reconstructed exponential equation, we'll use lambda is equal to 3 to find f3 from both the original and reconstructed exponential functions. And if the 2 versions of f3 are both equal, then the reconstructed exponential function is more likely to be the original function and can be used to solve this equation and find the value of the unknown variable lambda. Here is f3 calculated from the reconstructed function, and here is f3 calculated from the original function. They are both very nearly equal, with just a bit of difference due to small errors that creep in from reconstructing the function. Now to solve this function and find lambda when f equals 0. We'll use this reconstructed function to solve for lambda. And we'll make lambda the subject of this equation. And we can substitute the values of a, b, and c into it, since the computer knows what they are. And so we solved the equation. And now to work with the cosine equation, where one of the terms is a cosine. We'll take this simple harmonic motion equation as an example. We'll use the same techniques as before to calculate f0, f1, and f2. Now we'll start with f0 and setting t is equal to 0 since we're trying to find t. And after substituting all the values in, we find f0. Similarly, we substitute all the values in and set t is equal to 1 to find f1. And then we similarly find f2. And now to find the constants a, b, and c of this equation from f0, f1, and f2. And after a lot of algebraic manipulation, it turns out that this is what b is equal to. And this is b's numerical value in this case. And this is what a is equal to. And this is what c is equal to. And this is a look at the graph of this cosine equation. And another function that mimics it is shown here in white. The frequency of this cosine function is very low. And we can check it for another point, say at t is equal to 3 and f3. And this is what f3 is from the original function. And this is what it is from the reconstructed function. And the two functions look the same, but the computer had to find a, b, and c from f0, f1, and f2. And now to solve this equation, we have to find the value of t when f is equal to 0. And we'll make t the subject of this equation. I like to call the inverse of cosine a cos. And so we'll substitute all the values in. And so this is the solution that we want. And so we have to check this solution, and we'll substitute it into the original equation. And it turns out to be a little bit different, but it's an extremely small number and very close to 0, so the solution is correct. So I hope that you have found this video helpful.